In this video, we are focusing on the strength of materials and mainly plastic deformation. So before discussing further, let us define what you mean by the strength of a material or when do you say a material fails. So in order to do that, we will do a test. So we will select the material. See, this is the material. Okay. This is the specimen you have right. So the specimen you are selecting is this one of this particular length L0. So you are doing a test on them. That means so you are attaching this specimen to here for grip. Okay, these are the grips, and you apply tensile stress here. Okay, you apply a load here, okay, and this L0 is defined as the gauge length. It is L0 is the gauge length. And you here the cross section is circular. Okay. You are selected a circular cross section material. So that means when you stress it, when you apply load at the two end and try to stretch it, that means it's deforms. That material deforms. That means as epsilon increases. Epsilon means the strain. So as strain increases, you can see that this length changes from that is initial length is L0, initial length L0 to instantaneous length L. So that change in length is defined as the elongation of specimen. Okay, that is how much the specimen elongation of specimen. And engineering stress is defined as engineering stress is defined as this instantaneous force divided by initial cross section. This is not that we are using the initial cross section. The cross section changes, but we are selecting the initial cross section area, and that is how the engineering stress is defined. It is given by the symbol sigma is equal to F by A0. It is the initial cross section area. And engineering strain is defined as elongation by initial length. Okay, initial length. So that is given by epsilon. So this is equal to delta L by L0 or equal to L minus L0 by L0, or it can be written as what is L by L0 minus 1. Okay, this is the stress and strain. Now we will draw a stress strain plot. Stress strain plot of a ductile material. A ductile material. A ductile material. So here on the y-axis you have the stress, and on the x-axis you have the strain. Okay. So let me draw this curve. So so you can see that as you increase the stress, the strain also increases. So this follows a straight line up to a particular point. After that, it dips and then it increases and goes like this, and finally it snaps here. That means the material breaks or fails. So this is string. Okay. Uh, let's note the important points here. So this up to here, this is sigma y. Uh, this is so sigma UTS. We will see uh, what are these, and this is your fracture point. The fracture point. Okay. And you can note that for this region, see, as you increase the stress and release it here, it will trace back this region. So this is called the elastic portion. Up to here, this is called elastic portion. As you cross the, so this portion is called the elastic portion. As you cross the yield stress, um, if you release it, it will not return back to its initial position. It will have a permanent strain left in that. Okay, so that point is called sigma y, or it is called the yield stress. Okay, that means beyond that point, if you increase the stress, it will not return back to its initial position once you release it. So this is the point where plastic deformation starts. Okay, plastic deformation starts. Okay, and this delta sigma by delta epsilon is the Young's modulus. Is the Young's modulus, or it is given by E. So this is applicable only for the elastic portion. So Young's modulus is defined as delta sigma by delta E. Okay, and this total area under the curve, total area under curve up to fracture will give you the toughness. Okay, will give you the toughness of the material. That is, area is given by that is equal to stress into strain. Okay, stress into strain. So that okay, so its unit is Newton meter per meter cube. So actually, it is Newton per meter square. So Newton per meter square, or you can write it as Newton meter per meter cube. That is joule per meter cube. That is energy absorbed per unit volume. Okay, that is given by the toughness. So let us look at some of the important mechanical properties derived from the stress strain plot. So first one, let us define what is strength. So strength is defined as the yield strength. Okay, yield stress sigma y, or sigma ultimate tensile strength, UTS. Okay, that is either sigma y or sigma z. Sigma UTS is the maximum load that this material can withstand. Okay, after maximum load is given, but the fracture occurs at a later point, at a lesser load, right? So the strength of a material is defined as at which stress it breaks. That means if you increase beyond yield strength, the plastic deformation occurs. We assume the material failed. Once the plastic deformation occurs, we take it as the failure point. So strength is usually written as yield strength, and taken as yield strength. And stiffness. So stiffness is given by Young's modulus, or E. Or E. That is, it is the slope of sigma epsilon in the elastic region. Okay, in the elastic region, we have seen that. Okay, so higher the Young's modulus means you need to have a higher stress to achieve a smaller strain. Okay, so stiffness is a kind of resistance to deformation. Resistance to that deformation, that is stiffness, right? Then you have the toughness. So what is mean by toughness? Toughness is the energy absorbed per unit volume before failure. Per unit volume before failure. That means up to fracture. Okay, to fracture. Right? That is the area under the sigma epsilon plot. Okay, then you have ductility. Okay, then you have ductility. Ductility is defined as the elongation strain at fracture point. Elongation strain at the fracture point. Okay, so these are the difference here. So ductility from here, you can see that. See, this is the plastic deformation, right? See, this is the plastic deformation to failure. So this gives you the a measure of ductility. Okay, so what exactly do you mean by this strength? You have defined strength as yield stress or as ultimate tensile stress from the sigma epsilon plot, stress strain plot. Strength means ability to resist plastic deformation. Okay, strength means it is the ability to resist plastic deformation. Okay, so that means if yield stress is high, that means you need to apply a very high load to have a to get a plastic to plastically deform the material. So what do you mean by stiffness? Stiffness is also ability to resist. It is the ability to resist elastic deformation. Okay, it is elastic. It is also the ability to resist deformation, but here it is the elastic deformation. It is given by the Young's modulus. That means higher the Young's modulus, you need to apply greater stress to have a elastic deformation. Okay, and ductility. What do you mean by ductility? That is ability to undergo the ability to undergo plastic deformation. Okay, is called ductility. Ability to undergo plastic deformation. That means if I draw two curves like this, that is epsilon, the one material exhibit a curve like this, and this another material here. If you look sigma and epsilon, you can see that see this goes like this. So you can say that this one is a ductile material, this one is a ductile material, and this one is a brittle material. So these are the differences between ductile material and brittle material.